I hope everyone can see my screen.
Yes, ma'am.
Okay. So this is the line integral, and as I told you that work done is the easiest example of a line integral that we can think about. Okay. If it's a closed curve, that is if you are starting from the point B1 and coming back to the point B1, moving about a curve C, then we are moving about a closed curve, and in that case the line integral is written in this manner. So this circular sign on the integration sign is the implication that you are moving about a closed curve. Okay. And then we had started doing a problem of which half we had done in class, and I had asked you to do the other half at home so that we can discuss the results and what are the implications of those results. So basically we were trying to discuss the concept of conservative and non-conservative force fields in terms of the line integral. Okay, so this was the problem given, that find the work done by the given forces. So there were two forces and you were asked to find the work done by these two forces in moving a body between two same points. So the starting and the ending points A and B are the same, but the forces acting on the body are different. One is F and the other is F prime. And these are the two paths given. Path 1 from A to B is a straight line, and path 2 from A to B is a curved line, and it was shown that it's basically a parabola. Okay, so we started with the first force, case 1. This is the force. So F dot dr will be this, xy dx minus y squared dy. And for the first path, the work done W1 is along the straight line from A to B. Now, as you can see that the straight line from A to B, this information you can see from here itself, that the straight line from A to B is nothing but x equal to 2y. So that dx equal to 2 dy. So what you do is, in the expression of f dot dr, you replace all the y's by x's. So you substitute the y values by their corresponding x values, and also the dy's by the dx's. Okay, so what you get is, in this integration, by putting the values of, by substituting y with x, and since x goes from, see from here A to B, x goes from 0 to 2, so you integrate between 0 to 2, and this is a very ordinary integral, and the final answer is 1. So work done by this force F in taking the body from A to B along the path 1 is 1 unit of work. Okay. Case 2 is not case 2, along the second path, that is along 2, C is a parabola of the form x squared equal to 4y. Okay, so now we have to substitute y in terms of this equation. So y is x squared by 4 and 2x dx equal to 4 dy. So dy is x dx divided by 2. All right, so that is the substitution that we have done in the expression of integration f dot dr. Again, x goes from 0 to 2, so everything is in terms of x, and if you calculate this, the answer comes to 2 by 3. All right, so what we see from here, first of all, we learn how to do this kind of an integration, that you substitute the value of x in terms of the path taken, and then you write down the boundaries of the one variable that you have kept in the integration, and you get the value. Now, another thing that we see from this particular problem is that the work done in moving between the same 2 points by the same force is different for different chosen paths. So the same force is doing the work on the same body in moving between the same points. However, the value of the work done comes out to be different when you have chosen two different paths. It's 1 for the straight line and it's 2/3 for the curved line. If you take some other form of C, you would see that you would get another value of work done. All right. Now, if you start from A, take the path 2 to reach B and again return to A via path 1, then what would be the work done? In returning from B to A, you are basically coming in the backward direction, the opposite direction. So W1 would be replaced by minus W1. So the work done is W2 minus W1, which is 5/3. So it is non-zero. Normally, from whatever knowledge of mechanics we have till now, we have been taught that when we start from a position and if we come back to the same position, then the work done should be zero. If you push an object and no matter how much force you use to push that object, if its displacement is zero, then the work done is zero. So we have learned up till now that unless there is a finite displacement, the work done is zero. However, in this particular problem, we see that even though the final displacement of the object is zero because it comes back to its original position, however, the total work done is not zero. It has a certain value given by 5/3. Okay. Now, case 2. Have anyone attempted to work out this integral for the second force? Has anyone tried this? If you have, then you can share your answer and then we will discuss the answer, the implications. Has anyone worked this out? No one? If you have worked this out, then please unmute and tell me. Your exams are not very far away, so you should, and our hands are tied. We are having to do these online classes. I don't meet you every day in college, so you should do some self-study using the material that is available from the book of Spiegel and etc. Because it is very difficult unless we have a blackboard to do a lot of sum and tell you how to do different sums. I can at most do 1 or 2 sums in this in such online sessions. Okay, since it seems that no one has tried this out, although it was a part of your homework to try out this second part, I'll show you how it goes about. So this is the other force F primed, and therefore F prime dot dr is 2xy dx plus x squared dy. So work done by this force is given by W prime, which is F prime dot dr. Okay. Again, for the first path along the straight line x equal to 2y, the work done is C1 F1 F prime dot dr. So what we do is we replace the y's by their corresponding x value. So y is equal to x by 2 and dy is dx by 2, and x goes from 0 to 2. So in the same fashion as we followed in the case of the first force, in the same manner we get the value of the work done by this force in going from A to B along the straight line is 4 units. All right. Whereas for the other path, that is the parabola x squared equal to 4y, you replace y by x squared by 4 and dy by x dx by 2, and x goes from 0 to 2. So the entire integration is in terms of x, and here again the value comes out to be 4. Okay. So the work done along both paths in this case are the same. The force F primed acting on the object in taking it from the point A to the point B along the straight line is 4, along the curved line is also 4, and you may try out any other form of C between these 2 points for this particular force, and you will see that the value of the work done will always come out to be 4. And if you bring the object back to its original position, evidently W1 difference W2 or W2 minus W1 will be equal to 0, because both the values of the work done is the same, that is 4. All right. So now we are going to note down some very, very important points from this particular exercise or this particular problem that we just now discussed. First of all, work done is different for different paths in case of the first force, right? Same force acting on the object between same set of initial and final point, but for different paths the work done comes out to be different. In case of the second force, work done is same for different paths. So definitely there is something that lies with the kind of force that we are talking about. Because we have chosen the same paths, we are working on the same object obviously, and we are working between the same initial and final positions. But for one force, the work done becomes different for different paths, and the second force, it is the same for different paths. So something is the matter with the kind of force that we are dealing with. In the first case, evidently the work done is path dependent, while in the second case, the work done is path independent. In the first case, the work done depends on the path chosen, so it is called path dependent. In the second case, the work done does not depend on the path chosen, so it is path independent. Okay. Now, the force fields for which the work done depends upon the path are called non-conservative. If the force is such that the work done by the force field between the same initial and final positions depends on the path chosen, that is, if it is path dependent, that particular kind of force is called non-conservative. This usually happens when there are dissipative forces present, like there is friction, there is loss due to friction, there is some loss due to heating, etc. There is some loss due to absorption. When such dissipative actions are present, then the force fields become non-conservative. Okay. On the other hand, if the work done depends only on the initial and final positions, that is only on the end points, regardless of the path connecting them, then the force field is known as conservative. Okay. So we get, by doing this simple problem on line integral, we get to know the concept of a very, very important categorization of forces, conservative and non-conservative forces. I'm sure all of you have heard about conservative. Can anyone give me an example of a conservative force field? Come on. Can anyone give me an example of a conservative force field? Yes? No one?
Ma'am, gravitation.
Yes, gravitational force field is a conservative force field. Why do we always, when the mechanics that we have been doing till now, till your class 12 exam, you have always known that unless there electrostatic force field too. So you have always known that unless there is a displacement, the work done will be 0. So we were actually at the back of our mind, without knowing about this, we were talking about this thing, that this exercise that we have done right now. We were talking about conservative force fields, which is why we always assumed that work done is non-zero only if there is a displacement, work done is 0 if there is no displacement. We were using this fact because we knew that we were working in a conservative force field. But now you know, we have shown using an example, doing a line integral problem, that there can be forces which are path dependent, and such forces are called non-conservative. For example, when a body of mass m is lifted up through a height h, the work done is mgh. Okay, so this work done is mgh irrespective of the fact whether you take it straight up from the ground through a straight line, or you walk around a spiral staircase and move up to the height h, or you have a slanting pathway through which you slide up the body. Irrespective of the path used, if it is lifted up through a height h and its mass is m, then the work done will be mgh, and this is irrespective of the path taken, which means that gravitational force is conservative. Similarly, someone just told that the electrostatic force field is also conservative. Okay, so from this single problem, we come to know about two very, very important things. One is that we cannot always assume that if the body is moving between 2 points, then the work done will have a single value. We have to know the path taken, and we also have to know whether the force is conservative or not. If the force is conservative, then you don't have to bother about the path taken. However, if you see that the force is not conservative, then you have to ask for the path taken. So if someone tells you, okay, this is a particular force acting on a particular body, and let's take it from this position A to that position B. Can you calculate the work done for me? What do you have to do now? Now that you know that there are two kinds of forces, you have to ask that person, is the force conservative? If he says yes, then you do not have to bother about the path taken. You directly calculate f dot dr, integration A to B. If the person says, yes, I think the force is non-conservative, then you have to ask for the path. If he says the force is not conservative, then you have to say, oh, then please give me the path taken, otherwise how will I calculate? It will depend upon the path. Okay, so is this thing clear to everybody? The path dependence of forces and when they are conservative and non-conservative? Is it clear to everybody?
Yes, ma'am.
Yes, because this is a very, very important concept. Okay. Okay. Now I will tell you a theorem and then we will prove it. And that again is a very, very important point from the theoretical point of view as well as a mathematical point of view, because you often get problems of this kind. So the theorem says that if a force can be expressed as F equal to grad phi, where phi is a single valued function and has continuous partial derivatives, then the work done in moving a particle from any point P1 having coordinates x1, y1, z1 to any point P2 having coordinates x2, y2, z2 in this force field is independent of the path joining the 2 points. In other words, the force is conservative. Okay, so what is the theorem? The theorem is that if we have a force which can be represented as the gradient of some scalar function phi, then such a force is conservative. That is, this force, the work done by this force in moving a body from any initial point to any final point will be path independent. Okay, so proof. Now work done in moving a particle from P1 to P2 is given by this, P1 to P2 F dot dr. In this case, it is said that the force is represented as grad phi. So we replace F by grad phi. So we have P1 to P2 grad phi dot dr. Okay. Now we write down the expression of grad phi. I hope all of you know by now what is the expression of grad phi. Del phi del x I cap plus del phi del y j cap plus del phi del z k cap, and dr is dx I cap plus dy j cap plus dz k cap. So work done becomes integration P1 to P2. This we have just expanded grad phi and dr. So we perform the dot product and what we get is this. Integration P1 to P2 del phi del x dx plus del phi del y dy plus del phi del z dz. But what does this represent? What do from our knowledge of partial derivatives, can someone tell me what is this? What does this represent, this expression?
D phi, madam.
D
Madam,
phi,
D phi.
yes, this is d phi. So basically, work done is equal to P1 to P2 d phi. You all of you know how to integrate this. Whatever be the form of the function, integrating d of that function will give you that function back. So the work done is phi at P2 minus phi at P1. But P1 and P2 are the initial and final positions. So you can clearly see from this expression of work done that it depends only on the initial and final positions. So if you know the expression of phi, then you just substitute the values of P1 and P2 and you get the work done. Okay, so we have proven the theorem basically, because since work done is just phi of P2 minus phi of P1, that is, it depends only on the initial and final positions. So the theorem is proven, which means that the force is conservative. So from this particular thing, we now have the knowledge of several very important things in physics. We are doing this as a part of our vector analysis syllabus, but this is of immense importance in any portion of physics and applicable in any portion of physics, any module of physics that you may study in future. Okay, very important. One is, from this result we can see that the work done depends only on the initial and final points. Okay, work done depends only on the initial and final points. Second, implies that it is independent of the path. See, in the expression of the work done, we do not mention the path taken whatsoever. We only know P1, we only know P2, and that knowledge is sufficient. We make no mention of the path that we are taking to reach P2 from P1. It may be a straight line, it may be a curve, it may be an infinitely looped curve, doesn't matter. We only need the knowledge of P1 and P2. In other words, it is independent of the path. Therefore, now that we know that if F is equal to grad phi, then F is essentially a conservative force because it is independent, the work done becomes independent of the path. So we can now say that conservative forces can be represented as the gradient of a scalar function. Conservative forces can be represented as the gradient of a scalar function. This scalar function is called the scalar potential. When you have the electrostatic force, which you just yourself mentioned that it is a conservative force, then the potential is the scalar potential related to it. If you take the derivative of the potential, you get the related field, electrostatic field, right? So this scalar function is called the scalar potential. Also, since the curl of the gradient of a function is always zero, if you have the gradient of a function, if you try to take its curl, you can work this out for yourself and see that curl of the gradient of a function is always zero. And in this case, F is always representable as the gradient of a function. So curl of this force is always zero. Hence, we also know the fact that for conservative forces, curl of F is always zero. So if you are given the expression of a force and asked whether it is conservative or not, what will you do? You take its curl. If it comes to be zero, then it is conservative. If it is non-zero, it is non-conservative. So from this fact, we also have now can make a very important statement. conservative forces are irrotational and vice versa. Okay. So since curl of a conservative force is always 0, so conservative forces are irrotational. Just a second.
Need to mixing number.
Okay. So what are the so this slide basically is a very important slide. Okay. In one slide we have proven a theorem and we have come to note down several very important facts about conservative forces. First of all, the theorem says that if we can represent a force field as the gradient of a function, then it should be conservative. So from our knowledge of partial derivatives, we have proven that. Because if the force is represented as the gradient of a function, then we have shown here that the work done becomes dependent only on the initial and final positions. In other words, the work done is independent of the path. When a work done by a force is independent of the path, that is when we call the force conservative. So we have proven the theorem. So from this theorem, we now come to know that conservative forces can be represented as the gradient of a scalar function. Whenever you see a force which is represented as grad of some phi, you can close your eyes and say that this force is conservative. And this particular function is called the scalar potential. Okay, this is one important piece of information that we get. The other information, very important information that we get is that since according to vector notation, the curl of the gradient of a function is always 0, and in this case the force is always representable as the gradient of a function, so curl of f is always 0. So essentially for conservative forces, curl f is 0. Hence, conservative forces are always irrotational. And it is true the other way too. If a force is irrotational, then it has to be conservative. So now if you are given a force and you are asked whether it is conservative or not, what you have to do? You have to take its curl. Okay. And if you are given a force, suppose this is a common problem. Suppose you are given the expression of a force in the component form xyz in terms of xyz, and you are asked state whether this force can represent an electric force, electrostatic field, or a magnetic field. Can someone answer me? You are given, I'll repeat myself, you are given a force and you are asked state whether this particular force can represent an electrostatic field or a magnetic field. What will you do? A very common Viva question. What will you do? Can someone answer me?
ম্যাডাম আরেকবার বলবেন?
You are given a force. হ্যাঁ বলো বলো।
ম্যাডাম ডাইভারজেন্সটা নেব, ডাইভারজেন্স এর।
Yes, ডাইভারজেন্স 0 হলে কি বলবে?
সলিডয়েডাল।
হ্যাঁ, তাহলে ম্যাগনেটিক ফিল্ড। আর যদি ডাইভারজেন্স 0 না হয় তখন কি করবে?
তখন ম্যাডাম কার্ল বার করব, দিয়ে ওটা যদি 0 হয় তাহলে বলবো যে ইলেকট্রোস্ট্যাটিক ফোর্স।
Yes, right, একদম ঠিক। So just from the expression of a force, so my question was this, for those যদি কেউ না শুনে থাকো, my question was this: you are given a force and you are asked state whether this particular force can represent a magnetic field or an electrostatic field. So you first take the divergence of the force. If you see that the divergence is 0, then yes, this is a magnetic field, solenoidal, and therefore magnetic field. If you see that the divergence is not 0, then what will you do? You take the curl. If the curl is 0, then it is irrotational and therefore it is a electrostatic field. Okay. So just from the expression of a force, you can readily say using your vector differential operators that you know whether the force can represent a magnetic field or an electrostatic field. Okay, so very, very powerful tool, and you have just now learned about some very, very powerful information regarding vector fields that you will require several times in several modules of physics in future as you go to higher semesters. All right. Okay. Now next, as usual, we will do a problem related to this. And this is a very typical problem that is often given in your exam. Okay. So this is a force in terms of in the component form and given in terms of x, y, z. You are asked to show that this force is conservative. Okay, so you know what to do. You take the curl. Next question is, hence find the scalar potential and also the work done in moving from a point 0, 0, 0 to 1, 1, 1. Okay, so you are given a force. First, you have to show that it is conservative, and then you have to find the related scalar potential and the work done in moving from a point 0, 0, 0 to a point 1, 1, 1. So what are the steps to be followed? Step 1, take the curl. You can work this out and show that the curl is 0. It is readily seen from here itself that the curl is 0, and therefore it is a conservative field. The moment you find that the curl of the force is 0, so it is a conservative field. Hence, we can write F equal to grad phi, where phi is the scalar potential. Clear? Next, we have to find this scalar potential. Okay. Now, since F equal to grad phi and F equal to this is the expression, so what do? We write grad phi is equal to this. So del phi del x I cap plus del phi del y j cap plus del phi del z k cap equal to 2xy minus zq I cap plus x squared j cap plus 3xz squared plus 1 k cap. Okay. Both are expressions of the same force. So now what we can do? We can equate the coefficients of I cap, j cap and k cap from both sides. Doing that, what do we get? We see that del phi del x is equal to 2xy minus z cube. So we can integrate, since the differentiation is with respect to x only. So what do? We integrate with respect to x only. So this is sort of a partial integration, although your mathematics teachers would come and put me into jail if they hear that I have told you this term partial integration, because there is nothing called partial integration. But if you think of this as a partial integration, it is easier to do the working. Basically what we are doing is we are treating y and z as constants and integrating with respect to x only. Okay, so that is what, in my terms, I'm calling it partial integration. But please don't use this term anywhere, because there is nothing like partial integration. Okay, so del phi del x is this. So you get phi by integrating with respect to x and treating y and z as constant. So phi comes to be x square y minus z cube x. But you have to write this. If you're integrating, there must be a constant of integration. And in this case, the constant may be in terms of y and z, because you have kept y and z, you have treated y and z as constants over here. Okay, so the expression will be like this: x square y minus z cube x plus some function of y and z that we don't know as yet. Next, we equate the coefficients of j cap from two sides. So del phi del y equal to x square. Del phi del y equal to x square. So phi, now you integrate with respect to y only, treating x and z equal to constant. So you get phi is x square y plus some function of x and z, because now we have treated x and z as constants. And then del phi del z equals to 3xz square plus 1. there should be a minus over here. It's a minus, so there should be a minus over here. I'm sorry, okay? So del phi del z is minus 3xz square minus 1. So again, now you integrate with respect to z and keep x and y constant. So you get phi as minus xz cube plus z plus some constant h of xy. Again, this I think should be minus z, isn't it? This should be minus z. Okay. Okay. So now if you compare the three expressions, so all these three are expressions for the same function phi. So if you compare the three functions, you see that the function of xy, that is hxy, is nothing but x squared y. The function of xz is nothing but xz cube. And the function of yz is z, doesn't contain y. So now comparing the three expressions for the same function phi, you can write down phi of xyz is x square y minus xz cube. It should be minus z, I think, plus some constant c. Now c is a pure constant. It doesn't depend on x, y or z. Okay, so this is the required scalar potential. And for step 3, you just put the values of the initial and final positions, that is 1, 1, 1 and 0, 0, 0, and the required work done. In this case, it has come out to be 1. It might be something different because I can see that I have made a mistake in doing the algebra. Okay, so are the steps clear to you, or do you want me to repeat it once more? These are the exact steps that are to be followed if this kind of a problem is given. This problem can be given in a different language also. You are given a force and you are asked to find the work done on an object in moving from one point to another. So the first step that you'll do is, even if they have not asked you to find out whether it is conservative or not, the first step that you'll do is you find the curl. If it is 0, then you don't need any path, you just need the initial and final positions, and you know that the expression of the work done is phi at final position minus phi at initial position. So you use these steps to find the expression of phi, the scalar function, and then using the values of the initial and final positions at the values of x, y and z, you put those values, substitute those values in the expression of phi, and you get the expression of the work done. There might be some mistake in the calculation here because I can see that I have not given the minus sign over here. But are the steps clear to you? Is there any confusion?
ম্যাডাম একটা প্রশ্ন করব?
বলো।
বলছি ম্যাডাম f সমান মাইনাস গ্রেড ফাই হবে না?
Okay, that is again a matter of, I mean, you can take f equal to minus grad phi. It doesn't matter if you don't take f equal to minus grad phi, because if f is equal to minus grad phi, then it doesn't, I mean, it would mean whether the work is being done by the force or if the work is being done on the force, whether the force is doing the work or the other way around. So if you are bringing a particle from, if you're talking about an electric field, there's a test charge, and if you're bringing a positive charge from infinity towards it, then the work is being done on the charge. If you're taking it away from it, still you are doing the work, but the work is being done by the charge. Okay, so it depends on whether the work is being done on the object or the work is being done by the object. That will decide the sign. So it doesn't matter if you take f equal to grad phi. It's not wrong. If you take f equals to minus grad phi, that is also not wrong. You can take either way. You can take f equals to minus grad phi, you can take f equals to grad phi. Okay?
Okay, madam.
Okay. All right. So So this particular problem is very important, and you can do similar problems from the book of Spiegel. There must be similar problems given in the worked out, and এখানে যে ভুলটা হয়েছে সেটা একটু rectify করে নিও. Okay. Now, so this more or less covers line integrals. The next step is surface integral. Now, I want to ask you, this is totally your decision. Do you want me to continue with surface integral? Because that again is a very important part and a bit difficult also. So do you want me to continue surface integral, or do you want to revise this part nicely, understand this, and then move on to surface integral?
It will be better if we revise it.
I think so, because first, you know, you do the line because I have the slides of surface integral ready, but I think that today we have learned several new concepts. We have learned the concepts of starting from line integral. We've learned the concepts of conservative and non-conservative forces. We have seen why, when a force is non-conservative, what happens. When a force is conservative, what happens. We have seen that for conservative forces, we can represent them as gradient of a scalar. That scalar is called a scalar potential. Such forces are always irrotational, therefore the curl is zero. So we have learned several small spots, but very, very important points, and all new concepts. I don't know if you have learned this anywhere else, but for me, these were all new concepts that I conveyed to you. So I think it is better that you revise these slides very nicely first and do as many as problems possible from question papers or Spiegel book or any other mathematical method books first. And then in our next class, we will do surface integral and volume integral. And also we will do the 3 vector integration theorems. Okay. So that will be, according to me, that will be better, because it's already, I think, yeah, it's almost, we have only 2-3 minutes left to 1 hour. So and so I think so we'll end today's discussion here. Okay, and I'll share the slides